Homework 34, page 352. Yes, we're going back to chapter 6, section 1. 5 through 31 odd, then 47 through 55 odd. That's like 19 or 20 problems. Okay, and now start with the question of the day. What is the area of a circle with radius r?
Pi r squared.
It should be pi r squared. Okay, that's what we've memorized, because obviously we've never proven this.
Yeah.
How do we prove it?
Wait, we talked about this a long time ago. And there was like you like broke it up into a bunch of tiny.
Well, how do we find, in our class, how do we find the area of something?
Well,
We take an integral. Of what?
function.
A
So I guess
function?
you just do the top half and then multiply by 2.
Okay, so now, so first off, what's the equation of a circle?
Should be 0.
Well, first off, hold on. Yeah, right. But let's just think about this. So we'll get there. First off, what equation am I working with here?
X squared plus y squared.
There you go.
Yes.
All right. Now, there is a way of doing sines and cosines with this.
Oh,
And-
polar coordinates, right?
You could use polar, or you could use parametric equations, right? With cosine as your x of t is cosine, and your y of t is sine t. But we don't know how to do integrals with parametric equations. You could try to be tricky and be like, maybe it's cosine of sine or something, and boy, does that get ugly quick. Because I thought, whenever I have a question like this, I think, what could they answer? What could they throw at me? You know, and once we get to, okay, we need an integral of what? Well, maybe cosine of sine of something. Sine. The problem is, and then you think, okay, well, because you want your x to, just like with a parametric equation, you want your cosine to be your y, you want your x to be your sine. So maybe you could do something like this where your cosine x is your sine. But then the problem is, okay, so then what are we integrating to? Well, sine would have to go from 0 up to pi over 2 to get all the way out to 1, and we could do the area of a circle, area 1. But then cosine of 1 is not quite there yet. He's not up to the 1, and so, or he hasn't come, and actually it would be parameterized this way where it comes back down. So he would need to be pi over 2, and maybe that works. And so I tried it. Oh man. I put in Wolfram Alpha. I just wanted to see what the antiderivative of this was. And usually if you just give it something crazy, it'll spit out something that looks like this. It'll be like where J is the Bessel function of third kind, and you're like, what is that, right? This, it actually said, like, it was no known, or it was like, no solution known with standard mathematical functions. I'm like, okay, well that's certainly not gonna work, right? Okay, so anyway, this is the way we're gonna go here. But what do we want to do? Because that's not a function. So what do we do?
Or I guess get y by itself.
Get y by itself first. Okay, so we take y squared equals r squared minus x squared. Then we take a square root, but now we have a problem, because when we take a square root, we actually get two functions here, right? There's one function. So I'm going to call one function the positive part, and I'm going to call the other function the negative part, okay? And we could see then when we graph these two functions, indeed, we get the full circle, right? We get from r to r, from negative r to r. This is the top half, f, right? Yeah. And it goes up here to r. And we could check that. Plug in a 0 for x. You get r squared, yep, that gives you r at the top. Okay, cool. So it's a circle of radius r. And then at the bottom, we get this guy here, and this is the object. we're trying to find the area of. He goes down to negative r, this is g of x. Okay, but now somebody just said, this is probably not the best way of going about this, right? We have two functions, yikes. So, somebody said to do something else.
Just take the top half.
Just take the top half, multiply it by 2, right? And that is probably what I would do. I would say, well, hold up, from negative r up to r. And so the area of the circle that we're looking for would be 2 times the integral of this function from negative r up to r. And even then, I would say, I'm going to take some antiderivative, then I'm going to have to plug in a negative, or I'm going to have to plug in r, subtract off plugging in a negative r. I could be even trickier and say, well, hold up. This is all symmetric. Each one of these has the same area. So if I find this area right here, I just multiply whatever that is by 4. So I go 4 times the integral of this function from 0 up to r. And that'll be the area of the full circle. And this is the way I would do it. Okay, that makes the most sense to me. It's going to be nice because you have a 0 there. Zeros, when you go to evaluate them, are almost always your friend, right? As opposed to plugging in the thing and then the negative of the thing, and then you got to hope that you're doing your subtractions the right way. It's a pain. So this is probably the most straightforward, the easiest way of computing this. But we're making a lot of assumptions here. One is that it's symmetric. Is it symmetric? Yeah, it turns out to be, but I don't really want to show that. 2, you're also assuming here that this is symmetric, i.e. that f is an even function, which it is, but one of you didn't prove that the integral of an even function over here to here, if f is even, then yes, indeed, it is equal to 2 times that, because f is even, and f does turn out to be even, because what did we say? F of x was root 1 minus, or sorry, r squared minus x squared. Plug in the negative x, you get the same thing as just the same thing. I mean, the negative. Plug in a negative and it doesn't change the function. Right? Plug in positive r, you get the same, or plug in. Right? Everybody got me?
Yes.
I'm just, okay. Okay, so this is making a lot of assumptions that we don't know. And in general, now, and this is what we're going to be talking about today. In general, you might have some function f and some other function, say g, and you want to know what's the area right here between these two functions. And that's kind of what we're dealing with here. That's what our topic for today is. That's what section 6.1 is finding the area of some region of the xy plane that's bounded by two functions. That region is defined by two different functions, the space or the area between the two functions. That's what we're doing today. And so, I figured we could do that right now. Like we could do that, or we could do that with this problem here. And so, okay, let's think about this. Let's just say we have some function, let's call it h, and we want to find the area from, say, A to B. What is the first step? The very first thing we have to do. Now, yes, we take the integral, but let's say we're thinking about a Riemann sum here. We're going to think about the definition of what an integral is. I want to compute from A to B, h of x, the integral h of x dx. That's a sum of something. In order to figure out what that sum is, what's the first thing we have to do? Do you guys remember?
Break it up into, tiny.
We partition the domain, right? In other words, we're going to cut it up, right? So, same thing here. I'm thinking of these as functions of x. So I'm going to partition the x-axis like this. Okay, now, no different here than what we did is we found the heights for each one of these. We could say here's some general one, say xn, and that height is this value right here. It turns out to be h of xn. And then we, and as we're doing our sum, we say, well then, each one of these depending on what delta x is, right? Delta x is the distance between here. Then that area, the nth area, is the height times the base, right?
Yes.
And so the height was given by h of xn times the base, which is always delta x. And so we get h of xn delta x as n goes from whatever to whatever. And then we take the limit, right? And that's what this means. So in the same way here, we're trying to find the area of this thing. And now we have, say, xn is right here. Now what height do we want?
R. Wait. Oh, f of x.
Yeah, so here's xn is here. But I want this entire thing. So I don't just want this top half of it. I want it to go all the way down here. Okay? And I want to compute this area right here. So how do I find this height right here? So in other words,
2 times xn. Wait, 2 times f of xn times xn.
Well, yeah, but how do we know? In general, you might have some f that's like this, and down here you might have some g that does this. So okay, what's the height then?
F of xn plus g of xn.
F of xn plus? So think about
times
it.
xn plus.
Well, hold up. If this, let's say the height is 5, and down here the height is -2, if I add them together, yeah, and now here's another thing. What if, thinking about my general function, my f is up here, and my g is down here. In every case, as long as you have the big function on top and the little function on the bottom, then the distance from here to here is always given by the top number minus the bottom number, right?
Yeah.
It's always top minus bottom, and you get your actual height, which is 2. So now this is key here. As long as you're sure that f is bigger than g, then that height that you're looking for is whatever the f is at that point, f of xn, minus whatever the g is at that point, g of xn.
All times xn.
And that's all times delta x, and we take the sum, which in the limit becomes an integral. What integral does it become? Hold on, I'm going to do limit, and big N up here, n goes to infinity. The integral of what?
It would be...
Let's start with from where to where. Where on the x-axis are we integrating from?
From negative
From negative r up to
r.
r of what?
F of x minus...
Mm-hmm.
Oh yeah.
Minus the integral from negative r.
Well, yeah, but just all together,
G of x.
whatever this happens to be, dx. Now, it might be the case that you could, of course, if you have two functions, you could split them up into two integrals. This is absolutely 100% equal to f minus g over the same whatever. That's always going to be true. But it might be the case that these things, like, cancel out, right? Like if your f of x is like x cubed plus 2x, and your g of x is like x cubed minus 2, well, you might want to go ahead and just do that instead of computing the integral of x cubed plus 2x and then minusing off your x cubed minus 2, because if you just keep them together like that, right? Well, now you've made your life easier. You say, oh, x cubed minus x cubed, just go on. And so now this is just 2x minus a minus is a plus 2. That's a much easier thing to integrate, right?
Yeah.
Than doing them both. So it may or may not be the case that you want to do this. in some cases, yeah, you'll want to do that. But always check to see if maybe it simplifies down to something before you go and do it. So now let's do that with this function here.
Yes.
Okay, so this will be the integral from minus r to r of f, which is the top half, so root r squared minus x squared, minus the g, which is negative root r squared minus x squared, which,
It's 2.
of course, like you've been saying this whole time, yes, it's just 2 times that. So that's plus that, which is the same thing as 2 times the integral of r squared minus x squared dx, which I'm going to go ahead and pull out the 2 and deal with this guy right now. Okay, so everybody see how I got from here to here?
Yes.
Okay, now I'm gonna get rid of this to give myself some space, but that's what we're working on now. We're gonna take the integral from minus r up to r, 2 times it, of root r squared minus x squared. And you can see it, excuse me, you can see, like, that is just that function, right? That's the integral of just that guy, and it's 2 times it. Yeah, it does work out that way, but in general, we can't count on g being the same thing as f, right?
Yeah.
If it is, or if it being negative f, if it is, then it does work out that way. But anyway, okay. So what do I need to do? How do I compute this integral?
You substitution.
Yeah.
Good luck.
Yeah.
UV.
Okay, do you see a square root?
Yes.
Does it
Yeah,
have stuff
typical
squared in it?
Oh, some trigonometric.
Oh, yeah, yeah. Oh, that makes sense.
Yeah.
Because it's circles. So
It's circles, right? But if you didn't know that,
yeah.
alright, so I like, okay, so I noticed that there's a minus there. So that means that this root's going to need to go in one of them. I like to put my root down here. That's just what I like to do. X is going to have to go here. And so if this is, well, it's not going to have to. I choose to put my X there. I could have flipped it, right? I like to have my X there. Why? Because, well, hold up. What is that?
R.
R, just plain old R, not R squared, right?
Yeah.
And that makes sense. Right?
Yeah.
I mean, okay, so, okay, now, I like to put my X here. Why? Because, how do what sine theta
Is X over R.
is just X over R, and now when I take the derivative, I don't have to worry about a negative thing. So I get positive cosine theta
Yeah.
d theta, and then that gives me what?
Um,
dx over r?
Yes.
Right, because that's the same thing as 1 over r times x, the derivative, yeah. And so, okay, all right. So, a few different ways we could do this. I like to just figure out, okay, that in terms of this, I guess cosine theta gives me the root r squared minus x squared over r, or I could bring the r upstairs over here.
yeah.
Yeah? Okay.
R will cancel.
And now, well, let's just see, right? Now, dx is the other thing I need. I have that right here.
Oh.
Dx, the r comes upstairs. R cos theta d theta. Now, I'm just going to substitute these guys in. 2 times the integral, and I'm not going to bother writing that. I could figure out what it is now. I'm going to wait till the end to plug in my r's when I get everybody back and find the antiderivative in terms of x. That's how I like to do it. Now, the root part is r cosine theta. The dx part is another r cosine theta. D theta, which is nice. We need that d theta there. Now let's go ahead and combine everybody.
R squared cosine.
So 2r squared,
You can pull that out.
which I could pull out because in terms of theta, he's a constant,
Yeah.
right? So we're not going to worry about him. Then what's left is cosine squared theta d theta, and what do you want to do with that?
Well, we can make it. Let's put 2 in it. Like, there's the trig identity that's like,
Oh yeah.
what is it? The sine one's easy.
1 minus sine over 2b.
It's like, there's a 1/2 times.
This is the one. This is the one I told you since trig to just be able to wake up from a dead sleep and write this one down.
Yes.
Much easier to integrate this way.
Yeah.
So that's what I'm going to do. I'm going to say, okay, 1/2 plus 1/2 cosine 2 theta d theta. Okay, let's do that antiderivative. We have 2r squared on the outside. Now, antiderivative of this with respect to theta?
1/2 theta.
1/2 theta.
Plus 1/2
No, just would be
sine.
yeah 1/2.
1/2
Sine.
sine 2 theta. But what is that? What happens to that 2
So
theta?
it's just
That
goes
2
away.
theta is going to have to come
1/4.
downstairs. Yeah, careful about that.
Yeah.
And now we're going to write it up here and make sure that's the case. Sine 2 theta. Here we go. Okay. Take the derivative of sine 2 theta. You get cosine 2 theta times the derivative of the inside, which is 2. If there was a quarter sticking out front,
You want
those would have canceled and we would have come back to here, which is what we want. Okay, good. Now, like I said, we could have gone ahead and plugged in our limits earlier. I don't like to do that, and this probably hurts me a lot because I do it this way. Whatever, this is how I like to do it. Theta, okay, hold up. Theta, arc sine, so theta equals arc sine of x over r. Okay, now this is going to look really bad here for a second, but just have faith. This actually is not hard at all, and you'll
Well,
see.
it's just gonna come out to like pi over 2 in the middle.
And then because
Well, it will, but we don't know that ahead of time, okay? So theta is arc sine x over r plus, don't want to mess that up, plus 1/4, actually it won't matter, sine 2 times theta is arc sine. Arc sine of x over r. That's important.
Wait.
All of that, right?
Yeah. Wait. Yes.
Yeah.
Now I could go ahead and figure out, okay, well hold up, arc sine is blah blah blah, and then 2 of it, and then that's an angle, so it's 2 times that angle. But we're not going to need to do that because we're about to plug in r's. And we'll actually, and notice, since it's x over r, it's going to be either 1 or -1, which will be really nice going into arc sine. So this is something, this is, like I said, this is going to work out just fine. Okay, let's do that. Let's do that up here. I'm going to get rid of all the work beforehand, and then we're going to evaluate this up here, okay? Alright, so here's all that work that we did. Now we have a 2r squared. I'm going to plug in my r and get something. I'm going to subtract off what happens when I plug in my negative r, right there. Those brackets are helping me because I don't want to mess this up, right? Okay, so when I plug in the r, let's just see what happens. Arc sine of x over r, when I plug in an r, I get arc sine 1.
Which is pi over 4. I think.
Uh,
Oh wait, no, pi
pi
over 2.
over 2.
Pi over 2, right?
Yeah.
Arc sine, plug in a 1, get out a pi over 2. Plug in a -1, get out a negative pi over 2. Right? Okay, so arc sine 1 is pi over 2. So plugging in my r gives me arc sine 1. That's pi over 2 and a half, so that's pi over 4. Right? Now, plug in my pi over 2 here.
So it's just
And I get
Plug in the-
1/4, and I'm just going to go ahead and write this out, plus 1/4 sine of 2 times pi over 2, right?
Pi.
Because this part here is pi over 2. So that's 2 times pi over 2, right there.
So that just goes to
It will,
zero.
which is nice. Now, let's do it this way. Now, the other way, we're going to plug in a negative r. Plugging in a negative r gives me negative r over r, which is negative 1. Arc sine of negative 1 is negative pi over 2. So that's negative pi over 2 times a half, which is negative pi over 4. And I add that to 1/4 sine of 2 times negative pi over 2. Okay,
Awesome.
also 0. And let's just formalize that here. This is the same thing as sine pi, which is 0. So this is a big fat 0. This is the same thing as sine negative pi. Sine of negative pi is also a big fat 0. So this reduces down to
I don't perform this.
2r squared pi over 4 minus a negative is plus a positive, which is 2r squared pi over 2. Those cancel and we get pi r squared as we expected. Nice! Now we've proven that the area of the circle. This is the first time you've seen an actual proof of that, I think. And we could have done it in the much easier way. Would have just been to do 4 times the integral from 0 to r of the original thing, r squared minus x squared, and you'd get the same thing here. And so, so on one hand, that assumes a bunch of stuff about symmetry that we haven't gone into, but doing it this way brings us to the topic for today, which is how do you deal with regions, okay? Regions defined by being between functions, right? So, here's one. Here's a region defined by 2 functions. Find the region, find the area defined by, this is how your book puts it, defined by the region enclosed by, and then you're going to have a function f and a function g. Okay, the function in this case is sine x and cosine x on, because I mean that's infinite, right? So I have to say on x equals 0 to x equals pi with every single one of these. And this also applies when you go and do multivariable calculus, where you have some function in 2 variables, and so this is the output is some. You have an x-axis, you have a y-axis, and you have some region here on the xy plane that you're trying to integrate. It'll give you a volume. You see what I'm doing here?
Yes, I see, yeah.
Right? So like if you had a circle in the xy plane and you had some height above it, then you get, when you integrate that bad boy, you get the volume of this creature.
Yeah.
Okay? And even when you're doing that, you're going to have to figure out these regions, because one will be defined by some f, one will be defined by some g, and what you're about to do here is going to be exactly the same as we're doing now. The step is draw the region, draw the region, draw the region.
Yeah.
I better see this in your homework. Okay? So we are on 0 to pi in the x-axis. So from 0 up to pi, we're looking at sine and we're looking at cosine. So sine does that from 0 to pi, right? That's sine. Cosine comes down here at pi over 2. So cosine starts here, comes down, and does this. Okay, so the region enclosed by, what they're talking about is the region between these two. So we have this part here, and up to pi gives us this part here. Alright, now you'll notice that in one case, one of these functions is bigger than the other, but then it switches, doesn't it?
Yeah.
Right? So it starts off, sine is bigger, is the bigger function, but then it gets smaller, right? Or, sorry, cosine, this one's cosine.
Yeah.
This is cosine. Then, sine starts off smaller, then he gets bigger, right? There's my sine. So, what I suggest you do is that you find where it switches. You find this point right here where it switches, and think about, okay, let's call this area 1, and we'll call this area 2. Where do these two meet?
Well, sine is x equals
Pi over 4. That's where it is. I shouldn't need to explain that. Alright, pi over 4 is where they're equal to each other. Okay? And so we're going to split this up into two different integrals. We're going to have area 1 given by an integral from where to where?
0 to pi over 4.
0 to pi over 4, and then we'll figure out what we put there. And then we'll have area 2, which is this area, given by the integral from where to where?
Pi over 4 to pi.
From pi over 4 up to pi. Now, that area, again, is the difference between those two functions. And as long as the bigger one is the one that you're writing first, and then minus the smaller one, then it doesn't matter if they're positive or they're negative. If the bigger one's on top, the smaller one's on bottom, then you go that one minus that one.
Yeah.
So over here, what do we want? What minus what?
1 minus...
Cosine of x minus sine.
Cosine x minus sine x on that one. And now over in this region, we want what minus what?
Sine of x minus
The
cosine.
bigger one minus the smaller one, which in this region is that guy right there. Alright? So let's do it. Let's compute area 1 is what? Antiderivative of that is...
Negatives. No, just sine.
Yeah, good. Just sine. What about that?
Cosine of x.
Minus.
Plus cosine of x.
Minus,
No.
yeah, so minus a negative cosine, right? But yeah, I would just write plus. And then we evaluate that up at pi over 4 and down at 0. And this one is what?
Negative.
Yeah, negative cosine of x.
Yeah, negative cosine
Minus sine.
minus sine evaluated up at pi and down at pi over 4. Okay, so let's do this one. Pi over 4. So sine pi. I'm gonna write it out. Sine pi over 4 minus is plus cosine pi over 4.
Yeah.
So that's the first part. I minus off, plug in a sine 0 plus cosine 0. Okay, so sine pi over 4 and cosine pi over 4 we know are the same thing, and it's what? What is sine of pi over 4?
1 over root 2.
Yeah, 1 over what?
Root 2?
Yeah, right.
It's
Because
just-
that's that triangle. This one's pi over 4. So sine and cosine are both 1 over root 2.
So then it's 2 over.
So 2 over root 2, or 1 over root 2 plus 1 over root 2 is the same thing as 2 over root 2, which is root 2. Right?
Wait.
Because 2 is root 2 times root 2.
Yeah.
And then, but yeah, I hate that.
Wait. Oh.
Yeah?
Yes.
Yeah, who cares? I don't care. Okay, minus sine 0 is 0. Cosine 0 is
That's-
1.
Yeah.
So that's minus 1.
Yes. Yeah.
Right? Okay, now, so that's that part. And remember, we're adding these together because we want the total area as A1 plus A2. So we just got that A1 is equal to 2 over root 2 minus 1. Yeah? That's what we got there. Okay, so I'm going to get rid of some of this stuff so we can have a bit more room. Okay, can I get rid of all that? Okay, now working on A2. We're evaluating this guy. So I plug in a pi into this guy, and I get negative cosine pi minus sine pi. Subtract off, now I'm going to plug in pi over 4. Minus cosine pi over 4. Minus sine pi over 4. We just did that, and we found that that was 2 over root 2. So that's minus 2, right? Everybody follow that?
Yeah.
Right? Minus, yeah. Minus 1 over root 2 minus another 1 over root 2 is minus 2 over root 2.
Yeah.
Okay. Minus cosine pi is what?
Negative.
Negative 1.
Oh wait.
Right? Because cosine of pi is negative 1. So minus negative 1 is 1. Sine
It's just
is just 0. Okay, so that's the same thing as 1 plus root 2.
Yeah.
Yeah, plus, because the negative 2 over root 2. Okay, so then area 2 is 1 plus 2 over root 2. Okay, so then the final area that we're looking for is A1 plus A2. Let's figure that out. The true area that we're looking for, because it says find the area, that's big A, is A1 plus A2, which is 2 over root 2 minus 1 plus 1 plus 2 over root 2. The ones cancel, and we get total, I guess, 4 of these guys.
Which is 2 root 2.
Which is, yeah, it should be 2 root 2. Let's just see. 2 times root 2 times root 2. Is that 4?
Yes.
Yeah, that's 4. And so, yep, 2 root 2. And I think that's what I got. And we could have made that simpler at the beginning. Whatever, who cares? Is that indeed? Yes, that's what I got. Okay? Now, here's the thing, though. Check this out. Okay, so there you go. There's your answer. It's equal to 2 root 2. Ta-da! Okay? Now, this same problem could have been phrased in a different way. I could have said, interpret the integral from 0 to pi of the absolute value of, and it doesn't matter which one, how about sine x minus cosine x?
Oh yeah. That would be
You'll see this in your homework. It'll say interpret the integral, and it's going to give you one of these. And what you do is you say, oh, hold up, absolute value. Let's not worry about that. What we're gonna worry about is these two functions. Same way, like you're always thinking, what region does this define? And you say, okay, sine and cosine. So you draw them on this domain from 0 to pi. And you say, well, if it's the absolute value, then the difference is always positive. The way to make the difference always positive is to take the bigger one minus the smaller one. And so this is the same thing as this. And it'll also say interpret it and then figure out what it is, and your answer is 2 root 2. Everybody get that?
Yeah. Because we just flip the other parts up and then.
Yeah, I mean, you could graph this and see it looks different. Like if you were to just graph the absolute value, nothing would come down below this. Like if you said, here's your function, and it's equal to the absolute value of sine x minus cosine x, it's going to look different. And that's why this means interpret the integral in terms of areas. And you could say, well, this function looks different. In fact, it's going to go to 0 here, because it's going to be the same thing minus the same thing.
Yeah.
You know? And so it's going to look funky, but if you take the integral of this function, you'll get the same thing as if you had done this right there. And somebody said earlier, when I was just drawing some functions and stuff, and you said, oh, it's the absolute value, right? It's like, how do you find the distance from here to here? Oh, it's the absolute value. Yeah, you could do that. Because it doesn't matter how far down this guy goes, right? Like, you'd say, oh, that's a negative area. Yeah, but not the way that we're doing it, right? The area in this case is always going to be positive because we've decided that we'll always take the bigger function minus the smaller function. So there is a way of reinterpreting that as an integral of an absolute value of stuff. But we don't need, that's hard. That's just hard. So if you could take this problem, because you graph that, I don't know, right? But what you could do,
Sine of x minus cosine of x looks like.
right? Yeah.
And then
And then you have to take the absolute value of it so that everybody pops up above the x-axis, and that's just a pain. But you could say, well, you know what? You're talking about this. That's a distance. That's always a distance. And so as long as I'm just taking whichever one's bigger as the top one and subtracting off the bottom one, I'll get the same thing. Everybody believe that? Okay, my job here is done. Actually, no, we got a lot to do. So here we go. Oh, yeah. Number 10. So all of these that we're going to, no, I'm sorry, the next two that we're going to do say, sketch the region enclosed by the given curves. Decide, oh boy, okay. I don't want to say all that yet. But it's going to say, sketch the region defined by the curves. And then find the area of the region. There's number 10. Now, in this case, they don't give you a limit on x. Like before, they gave you two functions, and they told you from, they said it's sine and cosine, it's between sine and cosine, and it's, I hate how they write this, 3 plus x over 3. And then they say between where x goes from 0 to 1. Here they're saying just the region enclosed by these curves.
So just like an indefinite
Well,
wait.
we gotta draw it out.
Yeah.
Okay, so this is the same thing as 3 over 3 plus 1 over 3x, or how about let's rewrite that as a third x plus 1, because I'm about to do an integral.
Yeah.
Things will probably be easier if I do this. So what I gotta do, what's my first step with any time I'm doing a region?
Draw it.
Draw it out, okay? This is gonna make your life much, much easier. So I'm gonna draw this out. This one, you know what root x looks like, right?
Yeah.
It looks like that.
Yes.
Right, it's a parabola. It's a parabola, but it's just been flipped, right? It's the inverse of a parabola. Nice, okay. Now this one, then he gets shifted up by 1 unit. So he goes here at 1. Anytime when you're doing these that you have the opportunity to put a point, an actual point with an actual number somewhere on there, it's going to make your life easier. So I suggest you do it. Now, 1/3 x plus 1 is a line. He goes through right here. Oh, nice. See what I mean? Nice. Like I have a point there, and I can be certain that when I plug in a 0 for this guy, he comes out here. And so now the only question is, does he go up like this or down? Well,
He's pretty
1/3. So
it's a third, right? So he's going to look something like this. Now you can see what they mean by the area enclosed. They're not talking about this area out here. Because you could say, I mean, I really don't need to make this argument, but I could. Like you could say, well, is it infinite? Because, I mean, you could imagine, you've seen before where you have something that gets closer and closer to something, and it's not infinite.
That's true.
Is this?
Well, they go different directions.
They are going in different directions, right? You could see, and we could make a formal argument, like a rigorous proof here that this distance is increasing.
But eventually, wouldn't the parabola pass the?
No.
It would.
No. Let's do it real quick. Let's call this one y1. Let's call this one y2, and let's take their derivatives. y1 prime is what?
1 over 2 root x.
1 over 2 root x. y2 prime is equal to what?
Just 1/3.
1/3. So as we go further this way, this slope gets smaller and smaller and smaller. This one's always 1/3.
Oh.
And so, as you go to infinity, this guy's pulling off towards this way faster than that guy is going this way. He's always going up at a rate of 1/3.
Yeah.
Now we could like figure out that the distance itself between these two guys is increasing. We could write a function which gives me the distance between these two guys, take its derivative and find out that that is always increasing. That would be fully rigorous right there. I don't want to do that. I'm going to do it. So y2 is the bigger one, minus y1 is the smaller one, so that's the distance.
Yes.
And so the distance, the derivative of the distance, would be y2 prime minus y1 prime, which is y2 is 1√3, y1 is 2√x. And then whenever x is bigger than whatever it needs to be, this is going to be positive eventually, yeah?
Yeah.
Like let's just say that x equals 4. Then you have 1/3 minus 1/2 times 2 is 4, which is positive. Whenever it's bigger, this guy's smaller. And so he's always positive. So the distance between these guys is increasing. Okay, all right, there we go. Boy, we wasted a good 5 minutes there. But anyway, okay, so that's the idea. This area is infinite. That's not the area they're talking about.
Yeah.
We're talking about this area.
I guess
And
we find where they
so-
meet.
We have to find where they meet. And this is going to be the case when you do Calc 3 or whatever they call it, multivariable. You're always going to deal with this, right? Because like I said, you have some kind of region in here where two functions meet, and now we need to integrate from somewhere here to somewhere here. We also need to integrate from somewhere here up to somewhere here. And so,
I don't want to.
yeah, right? But it's the same problem. It's
Yeah.
like, okay, we need to find these points where they meet. So how do we find where y1 and y2
Just
meet?
like the substitution. Just 1 plus root x equals 1/3 x.
Oh, yes.
Yeah, we're saying where is it the case that y2 equals y1, right? At this point, whatever it is, this is where y1 is equal to y2. And so if y1 is equal to y2, we have 1 plus root x equal to 1/3 x plus 1. The ones are
Ones go
going.
away and it's square both sides. And then
We could square both sides, or another thing we could do is bring the 3 upstairs and then bring that guy downstairs. And you'll end up with the same thing, because that
It's
is
just root
that.
x.
And then you square both sides.
So it's 9.
So x is 9. Now, if you really wanted to, you could go find out that that's at 10. Right, plug in a 9 here, you get a 3 plus 1 is 10. If you're doing, like I just said, if this is a region in the xy plane and you're trying to find a function g, well then it might behoove you to figure out that this is at 10 and this is at 9, because then you want to integrate. You'll know that you'll want to integrate from 0 to 9 and 0 to 10. In our case, we don't really need it, but it's nice to check. Plug in a 9 here.
you
Uh-oh.
get 4. Oh, it is 4 for the other one.
Ah! Boy! Okay. Plug in a 9. You get a 3.
Yeah.
Plus 1 is 4. Boy! Okay. Plug in a 3. Divided by 3 is 3. Plug in a 9 divided by 3 is 3. Plus 1 is 4. Okay. So then you'd be integrating up to 4, and you would have just gotten marked off because you did the thing. Okay. Okay. So that's one way of doing it. Now we know this. So now what am I integrating? From where to where, and what minus what?
So the bigger one minus the
0 to.
Yeah, it's 0 to 1.
Okay, so from 0 to 9 in x, and then what minus what?
1 plus root x minus
1 plus
1/3
root x minus, don't mess this up. It's minus the whole thing.
Yeah,
It's minus the whole thing.
1/3 x plus 1.
Is there a simplification we could use?
And the 1's go away.
Yeah, that's nice, right? Instead of computing the two separate integrals, you could go, oh, in this case, this works out to my benefit because the 1 minus the 1 is gone. And now I could just say 0 up to 9 of root x minus a third x dx.
Now please put it on. Or, no, never mind. That's just x.
Negative 3 have 2/3.
So, 2/3
Yeah, 2/3 x.
x to the 3 halves minus
2/3 x squared.
1/6 x.
aha.
1/6. Yeah.
So
right,
let's
right.
check. Okay, take the derivative of this. 3 halves drops down, kills the 2/3. Subtract 1 off of that and you get 1/2. That's what we have. This, the 2 drops down, leaves me a third. That goes down to 1, gives me that. Okay, nice. 9 and 0's nice. I love 0. In this case, we get 2/3 cubed root 9.
Yeah.
Right? That's what 3 halves means. Take the square root and then cube it, or the other way around. This way works. Nice. 1/6, 9 squared, and this works out to. I'm not gonna do this. I did it by hand, and I got it wrong like 3 times.
Wait, so it's like 2/3 times.
It's 9 halves. It's 9 halves.
Oh, yeah.
It works out to 9 halves. So, 9 halves is the area of that region. Now here's the here's the thing, and this is what In this case, the other way of doing this, it's about the same amount of work, but there are cases where you want to do it the other way. The other way of doing this is to reinterpret this as x as a function of y. That is, this picture, we flip it, although you wouldn't start here. You would say, well, hold up. Let's look at what we have. So I'm going to go ahead and put 9 halves here because that's what we got for this guy. Now what you could do is say, well, hold up. Do I want to think about these as functions of x or functions of y? And if y equals 1 plus root x, we could solve, right, find the inverse of this function, and we get y minus 1 squared equals x. There's my one function. On the other hand, we could get if y equals, the way they wrote it was like this. So this is what you're given. You might think, it might be easier if I get this in terms of that. And now I get 3y minus 3. So there's my one function. There's that. Now I just reinterpret these guys and I draw them
They're the same.
as they are exactly the same thing. Now I'm just saying, okay, well, x, so if x equals y squared, that's just the parabola of this guy. So y minus 1 will shift him over 1, like this. So he's that guy.
Be like. Wait. Oh wait. Oh yeah. Yeah.
So
X
here at
equals
1.
Y squared, but isn't x equals y squared facing the other way?
Well,
'Cause y.
but not the way I've drawn it.
Oh,
Yeah.
yeah.
Y is the input axis now.
Yeah.
But you could see, this is the same thing if you flip it, right? If you flip the x and the y, he pops over there, and what have we done? Well, when you take a square root, you either take the top branch or the bottom branch. Here they've taken the bottom, or the top branch, right? So like, given this, you could take a square root, and when you do that, you get y minus 1 is equal to plus or minus root x. The minus root x would correspond to this guy who's not there. Right? Okay. Okay, so that's that guy. The other one is just x, it's just a line. So he goes down to minus 3, and he has a slope of 3, and he goes through there. Yeah, okay. And then he goes through again. And now you have the same problem, and you say, okay, hold up.
At 10.
Or at 10, right? And now you go, okay, hold up, where do they cross? I want to know where they cross, so I'm going to set the x's equal to each other. I'm going to say, where are the outputs of these two functions the same? Where is x1 equal to x2? Well, x1 is y minus 1 squared. x2 is 3y minus 3. Multiply it out, so y squared minus 2y plus 1 is equal to 3y minus 3. So now we get y squared minus 5y. Did I do this right?
Plus 4.
Plus 4 equals 0.
Yeah.
And I can
There's
probably,
two.
hopefully
So
factor.
negative 1 and negative 4.
Oh, there's two.
Yep.
Yeah.
Y and 1 and 4, and both negative, that should do it. So I get when y is equal to 1, or when y is equal to 4. Indeed, when y is equal to 1, they're both equal. And again, when y is equal to 4, which, lo and behold, is the same picture as that. Now you might ask yourself, okay, well then what's the output? Which again, we didn't need to know that to do this integral, we did not need to know that they went up to 4. Right? It didn't show up anywhere there. But it was nice to be able to check our work. Right? So I'm going to go ahead and just do that now. Plug in a 4. 4 minus 1 squared. So 4 minus 1 is 3. Square it, then x1 should be 9. Plug in a 4. We get 3 times 4 is 12 minus 3. X equals 9. 9. Okay, we got the right thing. Okay, so now I just need the bigger one minus the smaller one. So first off, where am I integrating from?
1 to 4.
Yeah.
I integrate from 1 up to 4 of what?
3y minus 3.
Right,
Yeah.
the bigger one is the line in this case. So now we have 3y minus 3 minus
1 minus 1 squared.
y minus 1 squared. Okay, dy, right, because y is the variable. Okay, we could multiply everything out. I don't want to do that. I'm just going to do this. Just so 3y, the antiderivative should be 3 halves y squared minus 3 should be 3y. Let's double check that. Take the derivative of this. 2, yeah. 3y just goes to 3. Okay, good. Minus u substitution. Just do a u substitution. And it would be u. Du would be dy.
Oh, yeah.
Okay, so then that's just 1/3 y minus 1 cubed. Check it. The 3 comes down, kills the 3, goes down to 2. Yeah? Take the derivative of the inside stuff. Oh yeah. That's the nice thing about having anything of the form x plus a raised to anything, or in sign, or something. You could just forget that it's plus or minus a. Yeah, right? And so, okay, I just forgot. Okay, so now I'm going to plug in a 4, plug in a 1, and I'm not going to do that. It works out to 9 halves. Okay, so either way you do it, can you, the piano.
So there are times when that method would be easier.
Yeah, and so right, I think the first method was way easier to do.
For this one, yeah.
Had you been given this problem, only they would have given it to you in terms of x and y here. It would have been given like this. You could say, you know what? It might be easier. But honestly, both of these ways for this problem doesn't really matter. There are some, though, that you'll see, you'll look at it and go, oh, it's going to be much easier if I just take the inverse of each one and interpret it like this. Guys, could you please keep it down?
Yeah, because if you ever have
Thank
like
you.
arc signing, you could just
Right,
do the inverse and
right.
it's just sine.
Yeah, like y equals arc sine x, and then your other one is something else, and it's like, well, hold up. Let's just see. Like, yeah, I don't want to have to integrate arc sine. That sounds terrible. Right? So, yeah, and so that's the idea. You use the context of the stuff. Okay, here we go. Here's number 8. Same thing, and now I'll read what it actually says. It says, Sketch the region enclosed by the given curves. Decide whether to integrate with respect to x or y. So after you've sketched it, go, which one of these is going to be easier? Draw, and then it says, and don't do this, it says draw a typical approximating rectangle, label its height and width. I don't care about that. Like, what they mean is after you've drawn your region,
Oh.
right?
Like,
Then you go, okay, I've decided I'm going to integrate. Oh, this, and like, here's something, right? Like, if they gave you something like this, it's like, well, hold up. Or especially if it looks like
Hey,
this.
what's the name of
This?
that? Yeah.
Well, that would be a parabola, but it's
I thought
it would be a parabola of the form y squared equals x. Yeah. Now, and then they give you something like this, and you go, okay, hold up. I'd have to integrate from here to here, and then from here to here, it's the function minus itself. From here to here, it's this, and then I have to find what this point is and what this point is. You know, it might be easier for me if I just reinterpret this like this, and then he comes from, where would he
Does it go through 0 or is...
Yeah, right. Let's pretend it does. That'll make my life easier. And then he goes from under the x-axis to over the x-axis like that, right? That would be a lot easier because then you're just saying, okay, I'm going to integrate from A up to B. And the whole time, this function's bigger than... the whole time, f is bigger than g.
Yeah.
Right? And so, this is what I mean. Once you have it sketched out, you sketch it the way they give it to
And
you.
those are really the same.
And then you say, yeah, like let's just call this
Oh, I
x
see. Oh, I see.
equals
Yeah, yeah.
y squared, and then this guy is some y equals mx plus b. Then,
Yeah.
or they could have given it, well, yeah, yeah, it's kind of obvious, like
Yeah,
this
I
one,
can see it.
yeah, and
It's
so,
just weird.
yeah, it is, yeah, sorry. So, okay, don't bother with the approximating rectangles, because then what they'd want you to do is this, and then you say, okay, I guess here's some x in somewhere, and so this is the approximating rectangle that I'm looking for. And in that region, see ya, if this is f and this is g, then the height would be f of xn minus g of xn times delta x. Don't bother with that.
Okay.
Like, I mean, you could if it helps you, but I
Yeah.
think it's just a waste of time because in every case, that's what you're doing. Every time you do an integral, that's what you're doing. Though, if you do that, it will help you with something we're about to do soon. But, yeah. Okay, again, sketch region, find area. Y equals x squared minus 2x. And y equals x plus 4. Okay, sketch the region. That's an easy one because that's the same thing as x minus 2. So I know he goes through at 0. I know he goes through at 2. And is he an upward or downward facing parabola? Upward. Okay. We know that because the leading term is positive.
Yes.
So he has to do that. Now the other one is x plus 4. So he goes through here at 4, not drawn to scale, but qualitatively we're good. He does this, and he does this.
Okay.
And so the region enclosed, obviously, is this region right here. From wherever this is to wherever this is. Those are the points we need. So we want the integral from wherever that, let's call it A, up to B, A, up to B. And this is obvious. Now, I don't want to reinterpret this way, because if I did, I can just kind of in my head here, we'd have my 0 and 2 right here. There would be my parabola. We'd have my A and my B up here, and he would go like, he would go through here at 4, Yeah, that's where they touch. He goes through at. See what I mean? This is terrible.
Yeah.
But 4, he comes down
Yeah,
to
down,
B.
and then
He goes up to B this way. There we go. This is where he touches. And
Oh,
so now you could see that, okay, I'm going to have to figure out what this point is. And up until there, it'll be this function minus itself. And then it'll be this function minus this function from here to here. That's a lot more work, right?
yeah.
Right, okay. So I don't want to do it that way. It'll be easier to do it this way. So, that one minus that one. So what do I write? What minus what?
X plus 4 minus x squared minus 2x.
Squared minus 2x. Okay, now let's find the a and the b. How do we do that?
Set them equal.
Set them equal to each other. So where is x squared minus 2x equal to x plus 4? I hope to get 2 answers here, because I can see that there's 2 places where this happens. So
and you will get so negative minus 3x minus 4 equals
minus 4 equals 0.
1 and 4 minus 4 and plus 1,
Yeah.
I think.
I think so. 1 and 4 should do it.
Minus 4 plus 1.
Minus 4 plus 1. We get x is negative 1 or x equals 4. That looks about right, the way I drew this, so that's nice. So up to 4, down to negative 1 is what I want. So from negative 1 up to 4 dx. Okay, now, it looks like this will simplify a little bit. We'll have a negative x squared. Negative negative is plus 2x, plus x is plus 3x, and then plus 4. Yeah? Easy enough, right? And so the antiderivative of that is a third x cubed plus 3 halves x squared plus 4x evaluated up at 4 and down at negative 1, which this was the one I kept messing up and kept messing up and kept messing up, and then I messed up again, and then I finally just like, what did I do wrong? Oh. Yeah, plus, not minus. And then it turns out to be 125 over 6. If you're playing at home, right, or if you're studying for a quiz and you're like, man, I'd like one to like actually work out, that there's your answer, you have an answer now, and you can do this one. So, there you go. Yeah, plug in your 4, plug in your minus 1, it works out. Okay. Okay, questions on that? So many of these problems just become clear when you just sketch the region.
Wait, so this is chapter oh, so there won't be any like
This
really
is 6-1. Yeah, they're not going to throw any crazy integration up to infinity at you.
Yeah.
But I will, because you can now. And we'll see soon something really cool. At least I think it's really cool. There's an object that I want to talk about. Okay, here's number 54. And actually, what is the prompt for this? I think it just says, sketch the region, find the area of the region. Okay, so the region is given by y equals sine x, y equals e to the x, and then they give you x from 0 up to x equals pi over 2. This is a cool one because it involves e, but it's also cool because of this. Well, I mean, it's not cool. It's instructive. It's instructive. So I'm going to draw the 2 functions. Sine does that. Starts here, comes up to 1, comes back down, and we're only going to pi over 2 anyway. So who cares? Now e to the x. If this is 1, e to the x goes through at 1, and he's positive. Like a lot bigger.
Is e or pi over 2 bigger?
It seems like it should do that.
2.7. Yeah, E would be bigger.
Yeah,
E should be bigger, right? Because I mean, you're talking about something 1 point. This is close. We could say close to 1.5.
Yeah.
And so then, since that's bigger than that, then that's bigger than that. So E is obviously bigger. And we know the slope's always positive, so he's going up. And so you think, well, wow, man, the region, nothing's enclosed. But it's defined this way. So this is the line x equals 0. He looks like this. This is the line x equals pi over 2. He looks like this. And so this is another thing that they could do to you. In multivariable calculus, they'll give you 4 functions. Right? Like I could have given you those 2 functions. I could have given you those 2 functions and then given you like 2 lines. Like a line,
like a parabola.
a line that, you'll have to, that's one thing you'll do, a parabola this way, and then like a line this way. And then you have to figure out, okay, from here to here, I'll integrate this over this, and from here to here, it'll be this over this, and then from here to here,
it's, or do you need,
say what now?
you could do that, it would just take a while.
It's straightforward.
Yeah.
There's the same way, like once you know your region, you just plug it into your integral and integrate. Same thing with multivariable. It's just there's more variables. So here's the one part, here's the other part. That's a line, and so now he's bounded. Now this region is bounded by 4 functions. 2 of them happen to be vertical lines, so they're not technically functions. But if you reinterpret them, they are. Okay, so yeah, but you don't want to do that here, obviously. It'd be much easier to integrate from here to here and then say that's the bigger one, that's the smaller one. So I'm integrating from where to where?
0 over 2.
From 0 up to pi over 2 of what?
E to the x minus
E to the x
sine of
minus
x.
There you go. E to the x minus sine x dx. Now, by the way, that's the same thing. It's exactly the same thing, because it's always positive, you're always taking, right? The absolute value means always positive. So you could reinterpret this and say, well, hold up, what's sine x? Boom. What's e to the x? Okay. And if their difference is always positive, then we're always going to take the bigger one minus the smaller one. The bigger one's always bigger than the smaller one there.
Yeah.
Right? Now, it would be different if we were integrating somewhere else, where you do this, and e to the x comes down like this. Then you might have to go, okay, hold up, where's this? And where's this? Because now it's going to change from here to here, sine's bigger, and then from here to here, e's bigger, and so then you have to figure that out.
So sine is just annoying, because it constantly changes which one's bigger.
Yeah.
Because it goes up and down.
But just like we did when we had sine and cosine, right? We just said, okay, hold up, and we could have kept going. Like we could have integrated out to like 5 pi or whatever. In which case, or I guess this is 2 pi, the way I've drawn it, 2 pi. I haven't drawn it right, but who cares? Then you just say, okay, hold up. Wherever that one's, we're just going to split them into areas here. Compute area 1, compute area 2, compute area 3, and over here, sine's bigger. Over here, cosine's bigger. And so as long as I'm taking the bigger minus the smaller, you're good to go.
Yeah.
Okay, in this case, e is always bigger. So what's the antiderivative of e?
E to the x.
Antiderivative of sine.
Negative
cosine. So e to the x plus cosine x, and we're evaluating that up at pi over 2 and down at 0. So that gives me e to the pi over 2 plus cosine pi over 2. Yep. Minus e to the 0 plus cosine 0.
Which is 2.
Hold up. Now. Yeah, it'll be 2. So that's e to the pi over 2. Can't simplify that. Plus 0. Minus e to the 0 is 1. Cosine 0 is 1. So that's 2. So it's minus 2. And I think that's what I got.
E to the pi over 2. That's pretty rational.
It's pretty irrational. Although, hold up, wait.
Oh.
No, not necessarily. Because they're both transcendental numbers, and if you take a transcendental and raise it to a transcendental, you might get a regular old number. So like, for instance, e to the I times pi is equal to -1. And so, yeah, that's the only way out. But if you know that what you have in there is not transcendental, like 5, then you could guarantee that this is transcendental. I don't think we ever really talked about what transcendental numbers are.
Like pi, just numbers that are. Wait, is it different than irrational?
Uh-huh. Oh yeah, they're all irrational. So you have your irrationals and your rationals, and never the two shall meet.
Yeah.
They are completely separate. But inside irrationals, you have another kind that's called transcendentals.
And pi is one. Oh, it means wait, they never repeat. But no, that's just, even irrationals do that.
Yeah. So, okay, basically, you give me any polynomial. Why not? We'll do this. Where all of the coefficients are rational numbers.
Okay.
All of the coefficients are rational numbers. If they're rational numbers, let me do this. If they are rational,
Then you could divide by one.
then
Wait, no.
the solution that makes this true, any solution that makes this true, is called algebraic. X is an algebraic number if it's the solution to a polynomial with rational coefficients.
Okay.
For instance,
Yeah.
0 equals x squared minus 1.
So it's just 1.
1
minus
equals x squared, so x equals plus or minus 1. So x is algebraic. But also, x minus 2. Is that a polynomial with rational coefficients?
Yeah.
Okay.
It's plus or
So
minus
2 equals x squared, x equals plus or minus root 2. The square root of 2 is algebraic. It's irrational, but it's algebraic. The algebraic numbers
But they.
can be rational, right? As in the case of any ax plus b. Is that a polynomial with rational coefficients?
Yes.
Okay, so then its solution
That's all.
is also a rational number.
Yeah.
In fact, all rational
Yeah.
numbers can be written like that, and therefore all rational numbers are algebraic.
Wait,
All
so
rational numbers are algebraic.
numbers that aren't rational or irrational.
Say again?
Are there algebraic numbers that aren't rational or irrational?
No, everything's either rational
Okay.
or irrational.
Yeah.
So I should have started with the reals and then said that that's completely divided by rationals and irrationals.
Yeah.
That is how they're defined. If you're rational, or then if you're not rational, then you're irrational. Okay, so that's what algebraic numbers are. They are solutions to these guys, and so they have forms like, you know, here we go, 1 plus square root of 5 over 2, or the golden ratio, phi. That is algebraic, because he's a solution to one of these equations, and I think it's x squared plus x plus 1, or there might be a minus in there somewhere. One of them's
That was
minus.
the one that was like 1 over x over 1 over, or wait, 1 over x plus 1 over x. Be like.
Yeah, you could rewrite that as 1 plus 1 over 1 plus
Yeah.
1 over 1 plus and so on. Then that is also the same thing there, right? And so those are the algebraic numbers. If a number is not or if there is no rational polynomial for which x is a solution, then it's transcendental. They're always irrational. Because every rational number can be written like this, and it therefore is a solution to some polynomial. There's your polynomial with rational coefficients. It's technically integer coefficients. It's the same thing. give me any 0 equals 1/3 x squared plus 7/5 x plus 9. Just multiply through by 3 times 5.
Yeah.
Right? And you'll get 0 equals 5x squared plus 3 times 7 is 21x plus 9 times 3 times 5. You could rewrite your rational in terms of integer coefficients, and so whatever, it doesn't matter. The point is, you have rational coefficients. That's the solution to it. So all rational numbers are algebraic. There are also irrational numbers that are algebraic. Also, is that a polynomial equation with rational or integer coefficients?
Yeah, it's x plus or minus I.
And so x equals plus or minus I. So I is algebraic. Okay, cool. So what about all the ones that are not solutions here?
Because you'll never get like a pi.
Right. So pi is transcendental. I'm not going to try. Pi is transcendental. E is transcendental.
And then like all the multiples of those, like
And so in other words, there is no way of taking E. So you could take root 2. Give me root 2. And I want to try to make something, somehow get him to equal 0. Well, what I could do is take it and square it, and then minus off 2. And that should give me a 0. In other words, I could take the number and either raise it to some power and then multiply it or divide it by something and get it back to 0. How can you get him back to 0? Or for instance, I have I. How do I get him back to 0? Well, I could square him and then add 1 and I could get back to 0. All of the algebraic numbers can be taken care of that way. There's no way of taking a transcendental number and doing that. You cannot take pi and then say, okay, let's cube them, and then maybe add, divide by 9, and then add what happens when I take them and square them and multiply, I don't know, by 3, and then hope to minus off 2 pi's and then add a 9 and get a 0. You ain't gonna get there. It's impossible to do. You can't do that with pi. Not without going out infinitely far.
yeah, because you couldn't.
Just like with E, right? Like, how could I take E and get... Well, if you go on forever, you could figure out a way of doing it, but not finitely. And that's what makes it transcendental. That's why I think that's why the terms use transcendental, because you have to transcend finite numbers in order, or finite expression to get there. So, there you go. All right. I know we're running late, but I do want to do this real quick, because this is so useful, and once we get it down in class, we could just use it. Let's suppose f is even. My claim is that then integrating f of x dx over a symmetric interval, so that would be something like from -9 up to 9, or from -91 up to 91, or from -0.91 to 0.91, right? And that's why I'm saying -L up to L is the same thing as going 2 times from 0 up to L of the same function. Now, graphically, let's think about this. If f is even, it means that he's the same over on this side, right? He's a mirror reflection over the...
Because when you plug in negative, it doesn't do anything.
Right. So in other words, you take your x, you plug it in, you get out your f of x. You get the same number if you went down to -x. If you went in the same direction to -x, you get the same thing. And so what you end up with is a mirror image over here. If f is even, that's the assumption. And so, if you're integrating from -L up to L, then this area, A1, is exactly the same as this area, A2. Right? So graphically, that's why this works. So you could just say, well, hold up. The actual area which is from negative L to L of f, is the same thing as 2 times the area from 0 to L, right?
Yeah.
So graphically, we have a sense of that. But that's not a proof. How do we prove this? Well, remember what this means. If f is even, then f of negative x equals what? Just plain old f of x. And so what I'm going to do here is say, okay, from negative L up to L of f of x dx, let's split this guy from negative L up to 0, and then from 0 up to L. Okay, now, I want to use the fact that he's even, and so how do I throw in a negative x? Well, hold up here. I'm going to do a u substitution right here. I'm going to say let u equal negative x. Or in other words, negative u equals x, right? Right. So then du is negative dx. Now, what does that do to my limits here? When x is equal to negative L, then u is equal to what? Positive L, because he's negative of whatever that is. Okay, and when x is up on the top, so I don't mess this up, when x is equal to 0, then u is equal to negative 0, or he's still just 0. So, now, I'm going to take this and go, okay, so L, negative L goes to positive L, 0 goes to 0, f of, now we're substituting u, but x is negative u, so he's negative u. dx is negative du, right? So negative, I'm going to pull the negative out front. Everybody buy that? That makes sense? And that kind of makes sense too if you think about, you have some even function like cosine, and you're integrating from negative 2 up to 0. Well, negative of it is the same thing as the positive of it. Now this is where I'm going to use my fact that he's even. Since f is even, this is the same thing as just f of u. So it's still from L up to 0, f of positive u du, because he's even. But now, integrating from positive up to 0,
The same thing as negative.
isn't it? So remember our thing here, if you switch these, what do?
Just make it
Make it negative. So I could flip the integration. Instead of going from L up to 0, I go from 0 up to L, but I have to make it negative. But it was already negative, so I make it positive. Right? So that's the same thing as f of u du. Okay? So all of that to say that this is equal to the integral from 0 up to L of f of u du plus 0 up to L f of x dx. We could do another u substitution here if we
Or
wanted.
you could just say,
Or you could just say, this is some number, if it's a t, right, f of t dt is the same thing as f of u du. Or let's just be really explicit. If u equals x, then du equals dx. And if u is equal to x, then L stays L, and 0 stays 0. So this is the same thing as 0 up to L f of u du. Now I do my substitution, 0 goes to 0, L goes to L. This is now f of u, dx is du. This is 2 times the same thing. From 0 up to L of f of x dx, because I don't care what. That's a dummy variable. I could have put a smiley face, it's the same thing. So, done. Now this is why it was the case that we could have just taken the top half of this circle. Since 1 minus, or r squared minus x squared is an even function, we could say that integrating from negative r up to r is the same thing as just multiplying 2 from 0 up to r. because he's even. Now let's do odd. And we're going to do this the same way. We're going to think graphically first. F is odd, and we're going to integrate over a symmetric domain. Okay, so if F is odd, I'm thinking of odd functions I know. Here's one. Okay. If it's odd, that means he's symmetric.
What functions?
I don't know.
Oh.
I was starting with sine, and I was saying, here's a function I know, and then I was like, Okay, so odd functions are symmetric with respect to the origin. So if we go up this way, we gotta go down this way. And then if he comes back down, he's gotta go up, and then do this, right? And what that is when you go over to, let's go to here, and say you go to x here, and you get out some f of x here, if you go in the opposite direction to negative x, then you get the negative of what that was. That is, that f of negative x is negative f of x. Right? So let's think of an odd function that we know. X cubed. Plug in a negative. That's the same thing as negative 1 cubed x cubed, which is negative x cubed, which is the negative of f of x. Right?
Yeah.
It's f of negative x. It's the same distance, but he's negative now. Right? Or if your x were here, and he's negative, there's your f of x. Now when you go in the same direction here to negative x, you plug him in, it's the same height, right? It doesn't look like the same height. It's the same height, but he's just negative now, or positive now, right? He has the opposite sign. And so you plug in a negative, you get the negative of what you got when you plugged in the positive. Okay, so what does that tell me about the integral?
Equals.
Because if he's positive over here, then he's negative by exactly the same amount over
Just
here.
equals 0.
It should, right? So in other words, if I integrate from negative L up to positive L of a, oh here it is. If I integrate from negative L up to positive L, then the negative should cancel out exactly with the positive, and I should just get
0.
big fat 0. That's what I should get. Now let's prove it. Same thing, I'm going to split up this integral. I'm going to say, suppose f is odd, and we're integrating on some symmetric interval. Okay, I could split them up. So I'm going to go from negative L up to 0 of f of x, plus the integral from 0 up to L of f of x. Now I'm going to say, okay, let's see, how can I make him negative? I guess I'll let u equal negative x, so that du equals negative dx, or how about like that?
Yeah.
Right, it's the same thing, doesn't matter. Okay, and so, now, when x is equal to 0, then u is equal to
Also 0.
also 0. When x is equal to negative L, then u is equal to
L. Right. Negative L, which is just
negative negative L, which is just L. So now, negative L goes to positive L, 0 stays at 0. And now we have f of x is negative u, dx is negative du, so I'm going to pull my negative out front, negative du. I want this to look like that, so I'm going to flip my order of or my limits of integration, so that it goes 0 to L. But then that makes that negative, which makes that positive, right? But f is odd. So f of negative u is the same thing as negative f of positive u,
And then pull that negative.
which is negative this integral here.
And then,
Do an x substitution and get negative 0 up to L f of x dx. So this thing is the same thing as negative from 0 up to L f of x dx. And then I add that to 0 up to L f of x dx. And what do we get?
big fat
Zero. Big fat 0 always, which agrees with our intuition, right? You have an odd function like sine, and if you're integrating from negative pi over 2 up to pi over 2, then the positive exactly weighs out with the negative, but now we could just use this from now on.